Students, good morning students. Very happy 75th Independence Day to all of you. So students, in yesterday's previous lecture, lecture 1, okay, I have given you informations about the terms, okay, and syllabus to be covered and examinations to be conducted. And also students, we have started with the introduction to D block elements, right? So in the previous class students, I told you position of the D block elements in the periodic table. See, in the periodic table, I told you that these D block elements, they are placed exactly in between that of S block elements and P block elements. Okay, right. That means group 1 to group 2 comes under S block, group 13 to 18 comes under P block, and group 3 to 12 comes under D block. And each of these D block elements contain 3 complete series: 3D series, 4D series, and 5D series. Okay, 3D series, 4D series, and 5D series. Right, students? So 3D series elements, I told you, they consist elements from scandium to zinc. That is what? Scandium, atomic number 21, to zinc, atomic number 30. Belongs to what? 3D series elements. 3D series elements. Okay. Next, I told you yttrium to cadmium. Yttrium to cadmium, atomic number 39 to atomic number 48, comes under what? 4D series. 4D series, right? Then next, lanthanum, atomic number 57, and there is a gap once again. Hafnium, atomic number 72 to mercury, atomic number 80. Okay, that is 5D series. Like this, 3 complete series: 3D, 4D, and 5D series. And the 6D series is an incomplete series. 6D series is a incomplete series, as already I told. Okay, but nowadays it is also almost containing 10 elements, because new elements are discovered that are to be included where? In the 6D series. Okay, students, see, in 6D series, actinium, atomic number 89, actinium. Okay, then atomic number 104 to atomic number 112, right? That is VH to CN, thorium to copernicum, that is 104 to 112, that comes under 6D series. Right, and I told you the definition, students. What are D block elements? The elements in which the last entering electron, penetrating electron, if it enters into D subcell, they are called as D block elements. And these D block elements are also called transition elements. Why they are called transition elements? Because why they are called transition elements, students? Because they are shifting their character, shifting their properties from what? Metallic to non-metallic. That means if you move from S block to P block, from left side of the periodic table to right side of the periodic table, as I already told you, these are placed in between what? S and P. That's why metallic character slowly, gradually changes to non-metallic character. There is a transition in character. There is transition in properties. From what? That is what? That is from metallic to non-metallic. That's why D block elements are called transition elements or transitional elements. But remember, students, all D block elements are not transition elements, but all transition elements are D block elements. Okay, all D block elements cannot be transition elements, but all transition elements are D block elements. Let us justify this sentence with some examples. Okay, right. But before that, students, I already have told you what are these transition elements. Transition elements means, just please try to remember, students. Now I will give you the definition. What are transition elements? Transition elements are nothing but, the definition I given you already. So once again I am repeating here, students. Transition elements. What are transition elements? The elements which have partially filled, okay, not completely, partially filled d orbitals in free state. That is, most elemental state is called free state, or in any common stable oxidation state. This is important. Okay, for most common stable oxidation state, these elements are called as what? Transition elements, because their character slowly change from metallic to non-metallic property. Okay, and these transition elements consist of 3D series, 4D series, 5D series. Scandium to zinc, 3D. Yttrium to cadmium, 4D. Lanthanum, then there is a gap, hafnium to mercury, 5D. And 6D series is an incomplete series. Atomic number 89, actinium, then atomic number 104 to atomic number 112. Okay, that is borium to, that is copernicum, comes under 6D, right? Okay. Let us, students, now move on to next part. Already I told you, general electronic configuration of d block elements is n-1d. Sorry, it's a noble gas, right? Noble gas n-1 into d. Just I will wipe it out, students, yes, because I want to give you general electronic configuration for each elements. General electronic configuration is what? General electronic, okay, configuration. General electronic configuration of d block elements is what? That is noble gas. Okay, noble gas n-1 into d, 1 to 10, ns1 to 2. Okay, it's not 4s, it is ns1 to 2. Okay, and this n-1d orbital, it is called as what? Penultimate shell. That is nothing but, when you compare s, p, d and f block, okay, it is called penultimate shell, last but one. If you move from s, p, d and f, last but one, that is called penultimate shell. Okay, right. This is what noble gas n-1d, 1 to 10, ns1 to 2 is a general outer electronic configuration of all d block element, 3d, 4d, 5d and 6d series, which belongs to what? Group number 3. Right. Now come to next, for 3d series. See, general electronic configuration for 3d series, very important for CET purpose. Generally, see, noble gas for this is argon 18. Okay, noble gas. And which orbitals are filled here? 3d, 1 to 10, and here 4s, 1 to 2 is the outer electronic configuration of 3d series element. That is from scandium to zinc. Okay, then 4d series. 4d series, what it is? Krypton, noble gas. Okay, that is 36. 4d orbitals are successively filled. 5s, 1 to 2 are completely filled. Then 5d series, outer electronic configuration is what? That is krypton. After krypton, what do you have? Noble gas? Xenon, 54. Right? 5d, 1 to 10, 6s, 1 to 2. See, these are the outer electronic configuration of what? 3d, 4d, 5d. Scandium to zinc, yttrium to cadmium, lanthanum, then hafnium to mercury. They obey these general outer electronic configuration. See, these are very important, especially for CET, Karnataka CET. They will already asked this one. Okay. In Karnataka city, they asked you particular general electronic configuration for 3D, 4D, 5D. Remember. Okay. Now let us move on to the next part, students. After understanding group, outer electronic configuration, what are the elements that they are belonging to this particular group? Next term is, say I told you, these transition elements. See, all D block elements are not transition elements, but all transition elements are what? They are D block elements. How? Let us see. Okay, after understanding this particular first part, now students, please try to understand all transition point to be noted. Note point. What is the note point? All transition elements, okay, are D block elements. But all D block elements are not transition elements. Point to be noted, very important for CET purpose once again, CET, right? All all transition elements are D block, but all D block elements cannot be transition elements. Why? Because see, that's why zinc, cadmium and mercury. Zinc, cadmium, mercury are called, what are they are called? They are called pseudo transition elements. Remember, pseudo transition elements, false transition elements. False, they are not true transition elements. Why? Because they are having completely filled d orbital. See what is zinc? In zinc 3d10. Okay, cadmium 4d10. Mercury 5d10. D orbitals are completely filled, neither in their free state nor in their common oxidation state. They are having partially filled d orbital. They are having completely filled d orbitals, so they are called pseudo transition elements. Remember, okay, very important for 1 marks. They are called pseudo transition elements. Give reason, because they are having completely filled d orbitals. So what is the definition? What is the character of transition element? They should have what? Partially filled d orbitals. Very important, students. This point to be noted. Okay, partially filled d orbitals in what? Free state or in any common stable oxidation state. That is stable oxidation state. Okay, right. Okay, this is the first beginning information. Right. Now after this, now I will come to what are the common properties of these transition elements. See, as physical properties is concerned, these transition elements, they are very hard, very hard, high tensile strength, okay, highly ductile, highly malleable, okay, high tensile strength, hard, brittle, high tensile strength, highly malleable, highly ductile, high thermal conductivity, high electrical conductivity, and even more number of unpaired electrons. These are the very common physical properties of what? D block elements or transitional elements. Only exceptional, zinc, cadmium, mercury, rest other, they show these properties. Okay, they are hard. Why? Metallic bond is very strong. They are hard, brittle, high tensile strength, highly malleable, highly ductile, high electrical conductivity, high thermal conductivity. Okay, and more number of unpaired electrons, right? Because of this, so they are having some unique character, differ from S block elements and P block elements. Okay, students. So this is the first information regarding introduction to the P block elements. Definition I told you, and also I told you what, why they are called transition elements, and what is the definition for 1 marks theory, students. This is the definition for 1 mark. They will ask you for 3. What are transition elements? Give example. Then you should be able to tell the elements in which elements which are partially filled d orbitals, either in their free state or most common stable oxidation state. They are called transition elements. Example, you can give any 3D, 4D and 5D series elements. Okay, right. So once again, students, now I will give you the information of all these series, how to remember them. Yesterday I given you, but still, once again we go for particularly physical properties. Okay, right. See first scandium. Okay, scandium, yttrium. Okay, then lanthanum, then titanium, zirconium, and hafnium. Okay, then vanadium, niobium, and tantalum. Okay, after vanadium, chromium. Okay, zirconium, hafnium, niobium, tantalum, right? Chromium, molybdenum, tungsten, manganese, okay, technetium, and rhenium, iron, okay, ruthenium, okay, then osmium, cobalt, rhodium, and iridium. After cobalt, students, see, now you will have nickel, palladium, and platinum. Commonly copper, silver, and gold. Okay, zinc, cadmium, especially mercury. Like this, you should be able to remember elements of 3D, 4D, and 5D series. Right? See, this is 3D series. 3D series elements from scandium to zinc. Then it is 4D series. Okay, yttrium to cadmium. This is 5D series. Okay, from lanthanum to first lanthanum, then hafnium to mercury. Yesterday I already told you. Okay, like this you have to remember 3 sets: scandium, yttrium, lanthanum. Scandium 21. Okay, 21 plus 18, 39. According to yesterday I told you magic number, right? Then once again 18, 57. But there is a gap here. 72, 73, 74, 75, 76, 77, 78, 79, mercury 80. Like this last we can write like this because there is a gap here. These are placed at the bottom of the periodic table, right? These are belonging to even anthelites and actinides. Now zirconium. Once when you write this, next is very easy. Go on adding 1, 22, okay, 23, 24, 25, 26, 27, 28, 29, 30. Right, this is over. Now 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. That's why I told you students, like this you have to make some trick and remember this particular series elements. Make a group of 3. First set, scandium, yttrium, lanthanum. Second set, titanium, zirconium, hafnium. Then third, vanadium, niobium, tantalum. Then next, this one, chromium, molybdenum, tungsten. That is derived from Latin name wolfram. Okay, then manganese, technetium, rhenium, iron, ruthenium, osmium, cobalt, rhodium, iridium, nickel, palladium, platinum, copper, silver, and gold. And lastly, zinc, cadmium, mercury. Like this, students, I already told you, zinc, cadmium, mercury, they are completely filled. 3D10, 4D10, 5D10. That's why they are called as what? Pseudo transition elements. Remember. Okay. Like this, in the group of 3, you have to remember along with the basic number, all 3D, 4D and 5D series, which I already have given you the general electronic configuration, which is very important for your Karnataka CET. Okay, Argon 3D10, 4S122, Krypton 4D10, 5S122, Xenon 5, that is 5D10, 6S122, right? Like this, you can remember, students. Okay. Now come to next another most important, and see what are the general properties of these transition elements. They are hard, malleable, ductile, high tensile strength, okay, high thermal conductivity, high electrical conductivity, and even more number of unpaired electrons. These are the properties of what? Transition elements. If the word transition come, means definitely these characters should come. And also they are having because of unpaired electrons, remember students, because of more unpaired electrons, okay, they are colored, they show color, different colors. Next, they are having tendency to form complexes, complex formation, okay, they are magnetic, okay, they show magnetic property, they are colored, they show magnetic property due to unpaired electrons. Even they show complex formation, cation and anion formation. High catalytic property, high catalytic property, okay, they show high catalytic property. Not only high catalytic property, even they form what? Complex compound, alloy formation and interstitial compound. Common character, they show variable oxidation state, color, magnetic properties, very, very important. Okay. Then complex formation, catalytic property, right? From complex formation, catalytic property, and lastly, interstitial formation of the compound. Interstitial compound they also form. And they also form alloys, mixture of two matter. These are the very important properties, physical properties of what? These all D block elements or transition elements. Okay, 3D, 4D, 5D, and 6D series I already told you. Actinium atomic number 89, right? To next atomic number 104 to atomic number 112. It comes under what? 6D, incomplete series. Right. This is about remembering the transition elements. Right, students? Okay. Now, see, I told you in this part what I told you in theory, one question. What are transition elements? Give example. CET 2 points I covered. See, all transition elements are D block elements, but all D block elements can't be transitional elements. Right? Zinc, cadmium, mercury, they are called pseudo transition elements because they have completely filled D orbitals. Okay. Then outer electronic configuration I given you, and what are the elements and what are their properties. Remember, once again repeating, high tensile strength, okay, hard, malleable, ductile, high thermal conductivity, high electrical conductivity. These are common physical properties. Other than this, they show because of more unpaired electrons, variable oxidation state, color, complex formation, catalytic property, high catalytic property, okay, high degree of catalytic property, right? Then alloy formation, and they also form interstitial compounds. So especially see this niobium, okay, molybdenum, technetium, ruthenium, rhodium, palladium, okay, these are having high catalytic property. Even see manganese, iron, cobalt, nickel, they also show very high catalytic property, and also some element that does not obey Aufbau principle. That I will discuss in the next property, that is called electronic configuration. Okay, right. So with this, students, I will move on to the next part in physical properties. First, all I told you commonly. Now I will go to first, as usual, electronic configuration of specifically 3D series elements they have mentioned in your syllabus. Okay, students. I think, students, you are saying the notes and taking down wherever necessary the points which I am writing as a note point. Note points are purely for your competitive examinations like Karnataka CET, NEET purpose, and even for JEE purpose. Okay, right, students. Now come to next property, electronic configuration. Electronic configuration. Electronic configuration of 3D series elements. 3D series elements, which is very, very important as per the whole basic chapter. If you know electronic configuration of elements correctly, you can easily understand this chapter, which is a very basic ABCD of this chapter. Okay, and also in first year you have studied structure of atom. Structure of atom you should know the electronic configuration, writing the electronic configuration of elements from atomic number 1 to atomic number 54 actually, up to at least 36, right? So out of this, see, first I am writing here 3D series elements, scandium. Okay, scandium, atomic number 20. Titanium, atomic number 22. Vanadium, atomic number 23. Chromium, atomic number 24. Manganese, atomic number 25. Okay. Then iron, atomic number 26. Right. After that, I'll write here, that is after iron, cobalt, atomic number 27. Nickel, atomic number 28. Copper, atomic number 29. Zinc, atomic number 30. Very simple, students. Just see here. First, I told you what is the outer electronic configuration. Noble gas N-1, D1 to 10. Okay, these are 3D series elements. Remember, what is the outer electronic configuration? It is 3D 1 to 10, 4s 1 to 2. Here, 3D and 4s orbitals are completely filled and 3D orbitals are successively filled. Keeping in that mind, we have to write here. So after C, calcium, atomic number 21, scandium. What is the noble gas? Argon. Argon 18. What do you write? 4s2, 3d1. Right? Okay. Next, like this. Next, this one. Argon 18, 4s2, 3d2. For what? Titanium. I like this for vanadium. Argon 18, 4s2, 3d3. And chromium, argon 18. Actually, it follow 4s2, 3d4, but it does not obey Aufbau principle. Last year, first year, we studied this Aufbau principle. Electrons enter into various orbitals according to their increasing energy levels, but some element does not obey Aufbau principle. This is what? Chromium. Therefore, they are indicated by star, asterisk marks. And even copper also does not obey Aufbau principle. Instead of going to 4s2, 3d4, it is 4s1, 3d5. Does not obey Aufbau principle. Leaving the lower energy orbital, that is half, jump to higher energy level. But still, these are stable. Why? According to Hund's rule. According to Hund's rule, half-filled orbitals and completely filled orbitals, they gain extra stability. Okay? Right. Then manganese. Once again, here, when you come to manganese, Ar18, 4s2, 3d5. See, once again completed. Iron, if you come, Ar18, 4s2, 3d6. See, this continue. Okay? Then cobalt 27, argon. Okay, 18, 4s2, 3d7. Right? The next after this, what comes? Nickel 28, Ar 18, 4s2, 3d8. Right? So once again, see, copper does not obey. Instead of 4s2, 3d9, what it is? 4s1, 3d10. Leaving the lower energy orbital half filled, jumps to higher energy level, but still stable due to completely filled d orbital. According to Hund's rule, half filled orbitals and completely filled orbital, they gain extra stability. Half filled orbital, they gain extra stability due to exchange energy within the same subcell. While pairing, they exchange energy. Higher the exchanges, more the energy lost. Lesser the energy, more the stability, which you learned in atomic structure in first year, right? Then here completely filled orbitals are stable. Why? Due to symmetric arrangement, right? Therefore, half filled orbital and completely filled orbital, they gain extra stability according to Hund's rule. Then coming to once again lastly thing as it is AR18 4s2 completely filled 3d10 over. So like this say here 3d orbitals here you are observing they are successfully filled. D1, D2, D3, D4 is not there, D5, once again D5, D6, D7, D8, say D9 is not there, D10, D10. D4, D5 not there because they does not obey outbound principle. In theory only, see this theory, these are important. In theory they will ask you this one. Chromium, the electronic configuration of chromium should be AR4s2 3d4, but it is 4s1 3d5, give reason for 2 marks. So write this one, electronic configuration, and write the explanation. According to Hund's rule, a filled orbital gain extra stability, hence it is stable, but it does not obey Aufbau principle. Does not obey Aufbau principle, first point you have to write. Then second point, according to Hund's rule, half filled orbital, they gain extra stability. Important. Point to be noted. Next year, if they ask you, the electronic configuration of copper is, copper should be AR4s2 3d9, but it is AR4s1 3d10, give reason. Here also, it does not obey Aufbau principle and it is stable due to Hund's rule as completely filled orbital gain extra stability due to symmetric arrangement. Here, extra stability due to exchange energy. Okay. Right. See this like this. See, you have to write. See here they will ask you the electronic configuration, but this electronic configuration further will help you in understanding all the properties, which is very basic. That's why I'm going you very slow. Now, based on this, how they will ask you the CET questions? Just observe here. Now you are given here, say this is the electronic configuration I written, this is before you. Now I will ask you one question. Please try to concentrate here, students. Suppose if you are given chromium, ground state electronic configuration of chromium is what? AR18, right? AR18 4s1 3d5. How many unpaired electrons are there in ground state? In chromium, when you write, this is 4s1 3d5, d1, d2, d3, d4, d5. You have to follow like this only according to Hund's rule. Always electron enter clockwise than anti-clockwise. So 6 electrons in the ground state. Name the element with the higher number of unpaired electrons in ground state. In ground state, remember that your answer is what? Chromium. Even in Karnataka CET and for 1 marks in theory, they will ask you this. Okay? Right. Then come to next. See, with the help of this outer electronic configuration, students, we can predict unpaired electron. That's why I told you in the beginning only. Unpaired electrons is the main character of what? These transition elements. How many unpaired electrons are there for scandium in ground state? D1, 4s2, completely filled. D1 means in d orbital, how do you write it? When you write this 1, 2, 3, 4, 5, this is D1. And D2, how do you write it? D1, D2. And D3, how do you write it? D1, D2, D3. D5, how do you write it? 1, 2, 3, 4, 5. D5 system. Up to 5, see, up to chromium. And is also 4s1, one more unpaired electron here, 6. Here they are paired up, right? And here D5 system, 4s2, 3d5, 1, 2, 3, 4. Manganese also containing 5 unpaired electron in ground state. D6, when you come to D6 from iron onwards, remember students, pairing of electron starts. I am writing only D part. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and this is D6. This is called D6. As electrons, see, as the number of D electrons increases, pairing starts. Number of unpaired electron decreases. Here 4. Okay. So here 1, 2, 3, 5, 5, 4. If you come to D7, remember students, D7, 1, 2, 3, 4, 5. First as usual, 1, 2, 3, 4, 5. D5, D6 and D7. How many? 3 unpaired electrons. Okay. As number of d electrons increases, remember, unpaired electrons decreases. 1, 2, 3, 4, 5, 6, 7, 8. Only 2 unpaired electrons. And here say almost D10. D10 means no unpaired electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? 6, D6, D7, D8, D9, D10. Here also D10. That's why this is very, very important. If you remember this will help you to understand even oxidation state, magnetic property. That's why I am writing here itself in the beginning, right? That is 1 unpaired electron in ground state for scandium, 2 unpaired electron for titanium, 3 electrons for vanadium, 5 for chromium. Okay? Sorry, 6 including s orbital, that is for chromium. Manganese 5, iron 4, cobalt 3, okay, and nickel 2. And lastly, copper, there is no unpaired electron in D, but it is having where? Ground state, where in 4s. Other s orbitals are complete except chromium and copper. Okay, that's why. And once again, see here it's pair up 4s to 3d10. Here also D10. D10 system, don't confuse. That's why I'm writing you D5 system. This is D6, D7, D8, D9, and D10. So this outer electronic configuration, I'm repeating students once again, very important for further discussion of what properties, right? And here they will ask you for theory, chromium and copper, 1 mass compulsory and very much repeated in Karnataka CET. Also, even sometimes NEET also, they will ask you this electronic configuration. Okay? Right. So after understanding now, see, outer electronic configuration of a 3D series and electronic configuration of each element from scandium to zinc, that is from atomic number 21 to atomic number 30. Compulsorily you should know. I am repeating. That's why I told you in the class in previous year, last year, in the theory class, while teaching this structure of atom, right, students? You should be perfect with the structure of atom, especially writing electronic configuration from elements atomic number 1 to atomic number 36 at least. Okay? Right. Now, see, this outer electronic configuration will give you regarding what size, unpaired electrons, color, variable oxidation state, magnetic property. That's why I am repeating. If you first this basic is good, then you can easily understand all remaining other properties of a transition elements. Okay? Right. Right. Then, see, generally, sir, Nayak sir used to tell us in first year only and ask us also to write a electronic configuration compulsorily. So please students, today only I am asking you, just write electronic configuration of elements from atomic number 1 to 36, especially for this 21 to 30, that is scandium to zinc. Write them in your notebook, practice them, then only you will come to know. Okay? Right. Without say wiping this, now I will tell you regarding second property. The first property, electronic configuration, is over. Okay? Right. Now students, I will come to next second property. After electronic configuration, size. Atomic size. Variation of atomic size. Atomic size of especially this 3D series elements. Atomic size of 3D series elements. Students, in this 3D series elements, remember atomic size. What is atomic size? Atomic size is expressed in atomic radius or ionic radius. What is the atomic radius? The distance between nucleus and outermost orbit containing the electron. Okay. So as the atomic number increases, distance between the nucleus and outermost orbit increases, especially for these elements. How does this size varies? Just I will tell you and try to complete this concept today. Okay. See students, after outer electronic configuration now, size, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, that is 164, 145, 136, 129, 137, 126, 125, 125, 127, and once again 137. These are the elements, okay, with the atomic numbers, and these are the atomic radii, atomic radius in picometers. Okay, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. See students here, just written this in terms of what period, across the period. You know that students, across the period, generally what happens? Across the period, generally what happens? Atomic radius increases. Atomic radius is increasing. Right? Atomic radius is increasing. Across the period, atomic radius decreases due to effective nuclear charge. You are observing. The atomic radii of these D block elements are smaller than S block elements, but more than P block elements. Why? Because these D block elements are placed between S and P. If you move from left to right side of the periodic table, atomic radii generally decreases. Why? Effective nuclear charge increases. As effective nuclear charge increases, electron cloud shrinks. As a result, atomic radii decreases. Right? So for 3D series elements, you are observing 164 to 137 atomic radii is decreasing across the period. But this decrease in atomic radii is not regular. See, from scandium to chromium, it is decreasing regularly. Why? Because as atomic number increases, number of unpaired electrons increases, effective nuclear charge also increases. But this effective nuclear charge dominates over number of unpaired electrons. As a result, electron cloud shrinks, regularly decreases. But for manganese, it is increasing. Why? Because of 4s2 3d5, more unpaired electrons. See, that's why, see, more unpaired electrons, they are not delocalized in covalent bonding, therefore increases. But once again, for iron, from iron, cobalt up to nickel, they are remaining. As in iron, number of unpaired electrons increases, d electron increases, pairing starts. Okay, number of unpaired electron decreases, but here screening effect, effective nuclear charge, and there is number of unpaired electron, both they balance each other. Therefore, from iron to nickel, they remain constant, remains the same. But lastly, you are observing from copper to zinc, they are once again increasing. Why? Because they are having 3d10, right? Electrons are adding to the same subcell. Due to electron-electron repulsion, atomic radius increases, right? So 3 in observation. First, decreases from scandium to chromium. Why? Due to domination of effective nuclear charge on number of unpaired electrons. Manganese and iron, they are increasing due to imperfect shielding of d electrons. Okay, and also they are not delocalized in covalent bond formation. Iron to nickel, generally cobalt, iron to nickel remains constant. Here because effective nuclear charge and number of unpaired electrons, both they balance each other, both they compensate each other, hence atomic radius remains constant. And lastly, from copper to zinc, they are increasing, actually should decrease, but they are increasing. Why? Because electrons are added to the same subcell. Due to they are added to the same subcell and completely filled. See, 3D, 3D10, and here also 3D10. Here 4s1, here 4s2. Okay, due to electron repulsion, atomic radii increases. This is how we have to explain variation of size. But in general, remember students, these 3D series elements, transition elements, are having smaller atomic radii, smaller radii than S block elements. S block elements, but higher, larger, we can tell, larger radii than P block elements. Okay, P block elements, because they are placed in between that of what S and P. Across the period, radii generally decreases. Therefore, remember students, smaller radii than S block, but larger radii than P block. So we will stop here. The next tomorrow's class will continue with the other properties. So thank you, students.